Well, welcome to CMSA, so Center of Math Science and Applications. So this will be a workshop on topology and quantum phase of matter. So historically, we started this center about 5 years ago with a big donation from a friend from China. And the idea is to form a center which is interdisciplinary between mathematics and other subjects. Not just in applied mathematics in traditional sense, but also in any fields that interest mathematics that we can build data. So this including physics, naturally, and engineers like big data or artificial intelligence, or biological, biomath and other fields. So we are very happy that this dynamic has been going on in the last 5 years, and we get a lot of help from many faculty from different departments, including some of you who are sitting here. And it's really very profitable to mathematicians and vice versa. So I'm very happy to see this conference is going on. And so it's amusing to me when I see that condensed matter is now using a lot of topologies and mathematics. In particular, it reminds me, Chern class is being used extensively in the subject. Chern was my advisor who passed away 20 years ago. But I read the history of Chern classes, and it was invented in 1940s. Wei, who was one of the greatest mathematicians in the 20th century, Andrew Wei made a remark. Is a Chern class is going to be used for quantizing physical field systems. This was 1947 when he read Chern's paper. And it was amazing that he felt it that way already in 1947. And lo and behold, now it's being used in all kinds of physics. So I'm very glad that they are being touched. And this shows that mathematician does have a heart for physics and other fields. And we certainly would learn something from physics also. So I'm very glad that we are running this, and Ashton has been doing a great job with others, and I'm very grateful for that. Thank you. So this
So I have only a couple of brief announcements before we get to the program. But before that, thanks to all of you for coming here this early, and for Yao and the center here for supporting this. So we're going to have a whole year-long program, and the idea was that many people who are not aware that there is the center, you get to come out here and hear talks and get to know the center better. So this was the idea of this kickoff workshop. So if you're interested in getting emails about these activities, you need to register. The same, if you've already registered, that's fine. We have your email. But if you have not, please register on the website. The website for the workshop has got a registration link. And yeah, so enjoy the workshop, and thanks to all the staff here, Sarah and others for doing a really great job. We're going to have some exciting talks today. So maybe I'll turn it over to Mohan from the chair first.
All right, so topology and condensed matter, as Yao said, is going to be the focus for the year. Topology and classical physics actually has a very old history, at least going back to the work of people like Faraday, Maxwell, Tate, who started thinking about various aspects of hydrodynamics, and then eventually led to Kelvin's hypothesis of vortex atoms and knots and so on. And that continues to this day in the context of hydrodynamics and vortices. But there's been a rejuvenation of ideas of topology in classical physics that we're going to hear about today from two aspects. One from President Prodan, who's going to talk about topological ideas in the mechanics of soft lattices, elasticity, and then from Professor Brad Marston from Brown, who's going to talk about the topological aspects of hydrodynamics, but instead of thinking about vortices, we're thinking about waves at the scale of the whole planet. So without further ado, first off, let's start the program.
Thank you very much for the invitation, introduction, and you say it's an honor to kick the kickoff workshop. So I'll tell you today that some new tricks that you can actually do with topological mechanics. And some of these tricks might take you by surprise. So let me start with the periodic table of strong topological insulators. The first version, let's say a smaller version of this table, came in 2008, and that was sort of a decade ago. I'm not sure how this is. So it's a decade ago, so it's sort of an old story, but the newer story is that some of these strong topological phases have been implemented with classical systems, such as photonic, phononic, in fact, with any wave supporting material. Now, if we look over what has been accomplished, we see that mostly people were working with the A-class in dimension 2, so that was the integer quantum Hall effect and so on, with BDI in dimension 1 and some versions of the A2 class in 2 dimensions. So these are the 3 classes that have been implemented classically. So as you can see, there are many other classes and phases which are not yet implemented classically. So in the first part of the talk, I will tell you how to implement all of these classes with mechanics, just passive mechanics, no Lorentz forces, high reversal braking, just the plane. And then I will concentrate on these classes which support Majorana modes, and I will tell you our experiments on, theoretical experiments on braiding Majorana-like modes with classical systems. So, classification table of strong topological insulators done with passive metamaterial. This is work in collaboration with Yankees, and he's sitting over there. So, yes.
What do you mean by strong? So, what is strong and weak?
So, the strong phases will be stable under strong disorder, and edge or surface or boundary modes do not localize under the disorder, yet the weak ones are unstable in the bulk, and also the surface states localize under any small understand. So to be concrete, in fact, I will implement the table with these sort of systems, starting with the most basic resonator. It's a disk with the center fixed and only one rotational degree of freedom. So that's the simplest resonators you can think. And one thing I want to point out, that if you connect this one with springs, then you have 2 possibilities which will implement a positive or a negative coupling. But other than that, the couplings are real. You cannot have complex couplings in this system. Now these guys, you can start them up and you can generate resonators with many degrees of freedom, and you can couple like so, and then you can put them in a lattice. So let's see if with such systems we can actually implement the whole table. In fact, this is not sort of a theoretical adventure. We are working very closely with the experimental group at New Jersey Institute of Technology, and here is how a real system will look like. So these are spinners with arms connected via magnetic couplings. So for example, just to give you a flavor, here is quantum Valley Hall effect implemented with this system, and there you see interface mode, as we all know will happen with quantum Valley Hall effect. Now, let me formalize a little bit. When I have a lattice like so, then the configuration of the lattice can be encoded in a function from the lattice to the internal, to the space of internal degrees of freedom. When I evaluate this function on a lattice site, it gives me the configuration of the spinors. So this one should think that they are stacked on top of each other. So I can define a scalar product.
I'm sorry, can you just tell us what you mean by a configuration of a spinor? What are the
So the
degrees of freedom?
configuration will be literally the angles, a snapshot of.
Okay,
the time snapshot.
okay, it's an angular variable for each.
That's right. There
Okay.
should be a reference line, which let's take it horizontal, and at some
Okay,
point of time,
and the velocities are not separate.
the velocity is not there. Because we will be looking in the small oscillation regime. So I can formalize this space of a function as a complex Hilbert space, and then the small oscillation, in the small oscillation regime, the equations of motion always look like so: omega squared times on the function which encodes the configuration is equal to the dynamical matrix. And the dynamical matrix is just an operator which we should think of as a Hamiltonian defined on that Hilbert space. It always boils out to such an equation. And now, if we are in this discrete context, the most generic form of this dynamical matrix is like so. So you have n by n matrix, which tells you how the fibers are rotated as one hops from a point x to x prime. Now there are constraints when you work with passive metamaterials. The entries are all real, but they can be positive and negative. And this D needs to have positive eigenvalues. Yes.
What's the difference between this and just springs and masses?
Will be the same, except that when you are in 2 dimensions, then the masses will usually have 2 degrees of freedom, and when you put springs, then these 2 degrees of freedom are coupled. The point of this thing is that the degrees of freedom are all decoupled, and they are accessible, so then we can make couplings at the net. So this one is extremely I think we hit the right framework, or the right
And again, you're making small oscillations about the rest then.
That's right. So this
There's
one,
not- there's
for
not-
example, is here. If I will keep this one a little bit, then you'll see this jiggling.
Right. But they're not spinning to begin with.
Not spinning, so that would be the nonlinear regime, which is also quite interesting. Maybe one more point, these things have a Q factor of 200, so when you slap one of these guys, it goes for a minute or so. So you really witness quantum mechanics on a lattice. It's completely equivalent. So let's see the mapping. If I start with any Hamiltonian from the classification table, then it will be also on a lattice, so it will take this form, and this Hamiltonian will have n degree. I'm not sure if we can fix this one. Maybe it's my computer.
They told me it may be just connection problem.
Yeah, okay.
3 minutes.
So here I am assuming that there are n internal degrees of freedom, like n bands, including the spin degrees of freedom. So now the map, which will take me from this Hamiltonian to a classical dynamical matrix, simply I replace 1 by the diagonal matrix 2 by 2 and I by this matrix, and this results in this map. It's sort of the easiest and the most straightforward thing you can do. One observation over there is that I'm only mingling with the fibers, so I'm not changing any of the hopping terms. Now there are several extraordinary things about this map. In fact, if I think as a map on a map from the algebra of operators from the original Hilbert space, in the algebra of operators of the classical Hilbert space, then this one is a algebra morphism. It respects multiplication and addition. So in other words, whatever algebraic manipulation I am doing with the quantum system, they will immediately translate into the mechanical system. It also commutes with a joint operation, and it's injective. As a result, it preserves the spectrum. And as you notice, I'm starting from a very irregular lattice, so periodicity is not assumed. The lattice can also have edges. So if this one has edge spectrum, then this one will also have edge spectrum. And if I cut an edge on this one, because in this map I am only mingling with a fiber, this one will also, so in other words, the map commutes with taking edges. Now there are some built-in symmetries. First, of course, complex commutes with complex conjugation, but there is this additional U1 symmetry which one cannot escape. Basically, if on the fibers I'm acting with this unitary matrix, then the unitary, the Hamiltonian, the map Hamiltonian is symmetric to that unitary transformation. The unitary transformation squares to -1, so that will divide my Hilbert space, the enlarged Hilbert space, into sectors which I will call minus and plus, and we have this sort of decomposition. And now if I combine complex conjugation with this U, I get a fermionic time reversal symmetry. So this fermionic time reversal symmetry has been sort of effective fermionic time reversal has been used in the past to claim that by such a procedure you get a system from A2 class, but in fact, because of this symmetry, you will never get a symplectic system, but rather a spin churn. So in other words, with this, if you stop over here, you are not able to probe the physics of A2 class. You will not be able to study, for example, the critical phenomena which should be described by the symplectic class, not by the unitary class. So we need to do much more to actually implement the system. And what is amazing is that indeed, if we have a symmetry which can be anti-unitary, it can square to plus or minus 1, and then the Hamiltonian commutes with this symmetry modulo a sign, then there is a certain way to actually implement this symmetry. It involves this sort of operation, and sure enough, when you restrict the map Hamiltonian on one of the sectors, the map Hamiltonian acquire that symmetry. So the message here is that if we are somehow able to excite the system and observe the system continuously in this sector, then the classical dynamics match exactly the quantum dynamics. So in this slide, I will tell you that in fact it's quite easy to, if you apply forces, then on these spinors, so you apply a field of forces, then the equation of motion in the frequency domain acquire right-hand side. And if you want to, of course, if I put here a generic force, I will mix these U1 sectors, but there is a way to project on it, which I can tell the experimentalist, okay, if you have this system, you have to do precisely what I say, and in that case, we will only observe dynamics in one sector. For example, if I am driving one spinner at position x0, the spinner alpha in this stacking, then all we need to do is to also drive the pair, and we need to drive the pair with an out of phase of t over 4. And if we do so, for example, we are staying in one of these. So let me show you how then, by this map, how this kind of system look like. So this will be the generating Hamiltonian for DNA class. That is the simplest one you can cook up. And for this one we need 4 stackings and this kind of connections. So recall that these are springs which, when looked from above, they look like so. Clearly it's quite complex, so it will take some engineering to actually do this in a lab. And then for the other classes we will need a stack of 8. Of course we look at the spectrum and all that to make sure there were no mistakes in the algebra, looking at the symmetries and degeneracies, and we can confirm that indeed what I've been telling you is like so. Let me show you in d equal 3. So this is, I can put all these 3 guys in with the same generating Hamiltonian, which is this. And again, I will need 8 stackings to actually implement this one with the mechanical system. Again, we look at the spectrum to make sure all the symmetries and degeneracies are as the theory predicts, and indeed it's the case. So now we have this tool at our disposal. How, if I am going in D class in 1 dimension, I am taking the Kitaev chain and I implement it with the classical mechanical system. Let me stay over here because now I hope I convince you that everything that we manipulate over here, that is braidings which are just Wilson loops, because rho is a morphism of algebras that we can port to the classical system. So here, if I changing this parameter in this fashion, then I am generating 2 domain walls. There will be 2 zero modes and 2 states trapped on these domain walls. So what will happen if I will braid these 2 edge modes, these 2 domain walls, using, for example, the T-junction? So a proposal for a qubit will be to have this actually a chain in the topological phase with just clean edges, and then we would like to, out of this clean edge, to morph it into one of these domain wall configurations, and we can do that adiabatically on the left side or on the right side. And then I would like to braid these domain walls and return back to this one and see what I get. Can I manipulate this qubit or not?
Why do you call it a qubit? I think it's classical otherwise.
So the qubit here will be just a Bloch sphere for me. So here I can load these 2 guys, they are mechanically. So I can load them with different amplitudes, but also with different phases. And then energy conservation will tell me that this guy will stay on the Bloch sphere, will have the radius of the energy. So now I have this vector which is on the Bloch sphere. Let's do the braiding, see where this vector basically moved. And what is nice here, why should we use the braidings and not some more direct, is because this will not depend on how exactly we do the braiding, if the braids are topological.
So could you maybe explain again, so what we now really have? So this zero, so what I should think of, you have this mechanical system, there's one thing I can move, which doesn't cost any energy. So there's just one thing, so I can make one type of movement, 2 types of movement. No, which
so it's one type. So this domain wall is literally deformation of the couplings. So I have this chain, they are coupled, but now I change the couplings and I force the chain to go from a non-topological phase to a topological phase, just through coupling.
Now, so the zero mode means now I can take one string, move it, and then the other, then nothing in between moves, and the other one on the other side also moves, or what?
So,
How should I vision?
so now, of course, if I change the couplings over here dynamically, I can move this domain wall. I can hold
I
this
don't
on-
want to move the domain mode, I just want to understand the zero mode.
the zero
So-
mode. The zero
so-
mode is just.
Can I just touch one of these strings and
That's
move it a
right.
little bit and then it doesn't?
No, no.
It's not oscillating.
This one, you can only load it. So in other words, you can pick the fidget spinner and shift it, and you all of a sudden you will see a mode. And if you take your hands, this will continue to oscillate. But that's all you can do. To move it, you
No,
have.
it's not oscillating because frequency is zero.
Well, this one is mechanics, so this will be mid gap. So it will be. The spectrum is shifted by some constant.
It's not a zero frequency state.
So in mechanics, to be stable, we need to shift it up by a frequency. So this will be, rather than zero, will be mid gap. But nevertheless, it will stay mid gap as I am doing the braidings.
Yeah.
So
Is this well defined or topological? So the frequency will now obviously,
no,
it's not
yeah.
stable under deformation of the frequency, huh?
So to do the braiding, all you need is a manifold in your Hilbert space, which is protected for the rest of the spectrum. And this is what this gives us. In the middle of the gap, I have these two zero modes, which stay exactly at the middle of the gap. And now I can do this
But
braiding
phase
without.
phase is now the phase of the oscillation.
So I can tell you immediately what will happen. So here I load these guys, they will start to oscillate and I will see them oscillating. Now if I start to change the couplings, I can adiabatically actually move this one back and forth. So if I change the coupling so that this domain wall start to appear here, it will take the domain wall with it and it will oscillate with the same frequency, but at the same time it will acquire a phase. And that phase is a geometric phase given by the adiabatic connection. So let me tell you why this is interesting. So why I want to actually go in these two different domain wall configuration is because we somehow identify.
Follow up on Akim's question.
Yes.
The frequency, does it change as you move it?
No, so
Protecting
so it will always be old, and there will be two states over here. And as
But the
I
whole thing is well above zero
yeah, all things
frequency.
is shifted from, so here it's equals 0, and this one stays in place, so this is constant. So by moving the domain walls, I actually can stay on a constant energy.
So you have some symmetry around that line.
That's right, that's the particle called symmetry, because that's what I
But
was
it's around
telling.
some arbitrary frequency. What's special about that particular frequency?
No, so when we do the mapping, of course when we do the mapping, the energy will be at 0, but with the classical system, you cannot have negative energies. So to implement this one in a lab, you need to shift all the spectrum up.
Mhm.
Just by coupling all these thinners with an external guy who gives it a non-zero.
So there's one term that breaks the particle.
Which is just the identity. So in other words, it's just, think of it, it's just Hamiltonian plus E times the identity. So we insert one of that term. In rest, this one has the particle force symmetry, so that's why this one is symmetric relative to mid gap.
So you don't worry that it might mix, things might mix between them?
So in here,
Like, strictly speaking, you don't have the particle symmetry anymore. Right? When you take things together.
so I don't have, but I do have, these ones are still protected relative to that. So in other words, I still have the protected manifold.
I guess the question is what protected means now. It's protected under the
Ah,
fine tuning
no,
of your
no,
experiment,
no.
or is it
It's
protected in
It's
some?
protected because these guys cannot escape in the bulk. So that's what the idea
But
about
the energy can shift, and the energy shift is also a phase
no,
change.
so energy will not shift here, so we can keep everything constant.
By fine tuning.
Well, because
Yeah, but,
you're
but
assuming
it's
that
not
the
fine
E,
tuning because these are metamaterials. You lock this in the couplings, so it's not fine tuning.
it's built in
That's
that,
right, in the
that you
couplings.
have
So the
identical,
metamaterials, you lock them in the couplings. unless you break these arms out of. So we found interesting fusion channels. So if we fuse two domain walls, of course, these zero modes will move up and we will lose them to the continuum. But quite interesting, if we fuse domain walls in this way, then actually the zero modes stay on. So, and then if we try the other coupling, all of a sudden with these domain walls we find fusion channels which either fit the Majorana fusion rule or the SE2 level 2 fusion rule. And that's why these braids in fact will give me something. So this here will be the T-junction, here will be the domain walls, and this, many of you have seen it, but it's a way to take these two zero modes and somehow do the same thing like you do when you turn your car 180 degree and come back in this configuration where you see the dot is on the left and the triangle is on the right. One caveat here is that we would like the Hamiltonian to return into itself. I'm here. So for that one, at some point we need to couple chains with different orientations. So this is special here. You need to rotate the superconducting parameter to make this connection without closing the gap. So nevertheless, this we can do numerically. We can compute the Wilson loop in the pi plus sector, and what we got is for when we braid this one, we get pi sigma 1, and when we braid this one, we get sigma 2. So for a 1 qubit, we can do the 90-degree rotation plus this sign. So we have also numerically studied what happens when we load into the T-junction scheme. Instead of one fermion, we load that configuration or this configuration, and we take this one, these two guys on the T-junction, and we obtain these braid matrices, which one could actually derive from the previous ones. We have not done this braid, which cannot be done with the T-junction, so I would like to exchange this domain wall with this domain wall, and this needs to go through another procedure. So we only, so you want the gap, so very important, you don't want to close either this gap or that gap, you want to protect. So then a lot of care needs to be taken up. So we have not, so you need to be able to connect this side to this side without closing the gap, and that will be a very special rotation. And at the end, if you can do this without closing the gaps, sure enough, if you unfold this one, you braid it B and C. So we are curious to see what we will obtain out of this. So in the end, this is where we are right now. I am not sure how far we can go with all this procedure. Maybe we can implement something interesting, maybe not, but we think for sure we can assist the program with real Majorana program. So I think we can learn a lot of things from this mechanical system, especially now that we have a way to implement them in the lab, a way to think a little bit much harder on how to implement the braidings. For example, this type of braiding, I haven't seen it in the literature, and so on. So I'll stop here and thank you very much.
More questions?
So maybe you mentioned this, like what applications do you have in mind for these?
So I'll be curious to implement just a simple algorithm. Let's see. So right now we are in the lab. We are just trying to move the domain walls, which from engineer point of view is not easy because you have to change dynamically the couplings. So that's one stage, so to move the nodes and make sure they come actually with they move as you want. And then if we have that in place, we can attempt the T-junction and see what kind of calculation. And I'm not in that terms. We will not bring anything new except that okay, we can do the mechanical version of a lower version of and a mechanical version of quantum computers.
Can I just push on that question a little further and ask, are there genuinely new things that you might expect to see in these classical systems?
No, because we all we started is with this mapping.
Yeah,
So there will not be anything new. Let me see. Maybe what was new here was this fusion rule, this one, which we could obtain it because we have control on the domain wall. So we can keep one domain wall in going from 2 to 0 and one from 0 to -2. So maybe that the fact that we have control over domain wall and then the domain wall in this picture actually carry an internal structure which I believe is labeled by SU2, and that's why I think it's this one which eventually will give me the framework for whatever I'm trying to do.
So it's very beautiful. But let me ask the question now on really the limits of this quantum classical analog. And I think, so the story in mind of what I've heard is that the thing which really stops a classic computer from working compared to a quantum computer, we both use wave mechanics, so that's the same. But what is different is this projective measurement part, which means that at the end we can't do error correction on any classical computer. I guess that's still true here. So that error correction algorithms can't be implemented. A lot of other things can be implemented, but not the error correction part, because this projective measurement is missing.
Yeah, that I could agree. So here, just to tell you a little bit what will happen if I do this braiding and I load the qubit like so. So at the end of what I should do is have these guys and a copy, an exact copy of it with the same vector. I will do the grading on this one and I will use the reference one to actually compare. So as I do the grading, then I should see the two shifted, and on top of that I should see the pi/2 phase between the
question, Bert?
What were the colors, if you go back to this graph,
this one.
no, the one you showed just, which had, what are the colors scheme, what does that mean?
So here I'm showing,
On the right?
this is time.
Yeah,
And
those are the energy levels,
there's the energy levels.
spectrum.
And on this one, here is the time, here is the chain, and here I'm showing how the chemical potential looks like as a function of time. So as you can see, it's in this picture, at some time, it starts from 2, then it drops to 0, then it comes back to 2. Therefore, I have a domain wall configuration which looks like this. Over here, the chemical potential starts at -2, then goes to 0, and goes to +2. Therefore, the domain wall configuration is like so. And as time progresses, I am diminishing the topological phase, and the fusion is over here. So when they are fully fused, you see the zero modes being lost. So that would be sigma equal vacuum, while here the zero mode somehow persists. And you will say, this is because maybe I put the domain wall, the mu to 0, where there is some symmetry. So in this graph, we put mu not at 0, but halfway. So this was 1, this was 0, we put it in the middle. It's true that I see some splitting, but nevertheless, I'm not losing the 0 modes into the continuum. So the manifold is still protected. And here you see again when I fuse one of these with its counterpart, then both 0 modes go into the continuum. It's lost, so fermion, fermion equal vacuum. And here is Majorana fermion. It will give me the, so that will be the colors.
Okay, I think we should carry on. So thank you very much for the talk.